Have you ever looked up at the night sky and wondered what secrets it's hiding? Out there, beyond the shimmering stars and swirling galaxies, lies a universe filled with mysteries so strange, so baffling, that even the brightest minds on Earth can't unravel them. Picture this: black holes that shouldn't exist, ghostly radio signals from deep space, entire galaxies vanishing without a trace. These aren't just plot twists from a sci-fi movie. They're real cosmic puzzles that keep scientists awake at night. And today, we're diving headfirst into 25 of the most mind-bending phenomena in space that defy all logic and explanation. Think about it. We live in an era where science has decoded the human genome, built artificial intelligence, and even photographed the edge of a black hole. Yet, the cosmos still holds onto secrets that leave researchers scratching their heads. Take the Great Attractor, for example, an invisible force so powerful it's pulling entire galaxies, including our own Milky Way, toward it at millions of miles per hour. No one knows what it is, or consider fast radio bursts, blazingly intense energy pulses that flash across the universe in milliseconds, only to disappear without a trace. Are they natural cosmic events or something else entirely? The truth is, space doesn't just challenge our understanding, it humbles us. But that's exactly what makes this journey so thrilling. Every unexplained phenomenon is a reminder that the universe is far stranger, far more wondrous than we ever imagined. And as we explore these 25 enigmas together, you'll start to see the night sky not just as a collection of distant lights, but as a living, breathing mystery waiting to be solved. So buckle up, because by the time we're done, you'll never look at space the same way again. Are you ready to uncover the secrets that even science can't explain? Let's begin. One of the most spine-tingling moments in the search for extraterrestrial intelligence happened on August 15, 1977. An astronomer named Jerry Amon was sifting through data from Ohio State University's Big Ear radio telescope when he stumbled upon a signal so extraordinary. He circled it on the printout and scribbled one word in the margin: wow. This wasn't just background cosmic noise. The signal blasted at a frequency of 1,420 megahertz, a bandwidth so narrow it couldn't be produced by any known natural phenomenon. Even stranger, it lasted a full 72 seconds, plenty of time to rule out equipment glitches, and then vanished. Despite decades of scanning the same patch of sky, it's never been heard again. So what made the wow signal so special? For starters, it matched almost perfectly with the kind of transmission scientists predicted an alien civilization might send. It was focused, powerful, and seemingly intentional. The signal originated from the direction of the Sagittarius constellation, about 120 light-years away, close enough, theoretically, for a technologically advanced society to reach out. But here's where things get eerie. No known celestial object, no pulsar, quasar, or comet has ever been linked to that exact location. Even after ruling out human-made interference like satellites or military transmissions, the mystery only deepened. Some researchers argue it could have been a one-time cosmic fluke, perhaps an undiscovered type of stellar explosion, or a bizarre reflection of Earth's own radio waves bouncing off space debris. Others, though, can't shake the possibility that we weren't alone in hearing it. What if something or someone out there was listening too? The wow signal remains a tantalizing enigma, a cosmic whisper that defies explanation. And until another like it appears, that scribbled note on a decades-old printout might be the closest we've ever come to proof that we're not the only ones staring at the stars, wondering who else is out there. If the wow signal left you questioning whether we're alone in the universe, dark matter will make you wonder if we even understand the universe at all. Imagine this: everything you've ever seen, touched, or known, from the tallest mountains to the farthest galaxies, makes up less than 5% of reality. The rest a cosmic shadow, Dark matter is the ghost in the machine of the universe, an invisible scaffold shaping everything we observe, yet slipping through our finest detectors like smoke through fingers. The first clues emerged in the 1930s when astronomer Fritz Zwicky noticed something bizarre about the Coma galaxy cluster. The galaxies were moving so fast that by all rights they should have torn themselves apart, unless something unseen, something massive, was holding them together with its gravity. Decades later, Vera Rubin's observations of spinning galaxies confirmed it. Stars on the outer edges were whirling just as fast as those near the center, defying the laws of motion. The only explanation, an enormous invisible halo of matter weighing down the cosmos like an anchor. But here's the kicker: dark matter doesn't interact with light. It doesn't emit, absorb, or reflect it. We can't photograph it, probe it with telescopes, or even say for certain what it's made of. And yet, its gravitational fingerprints are everywhere. Galaxies cluster in ways that shouldn't be possible without it. The cosmic microwave background, the afterglow of the Big Bang, bears its imprint. Even the way light bends around distant galaxies, a phenomenon called gravitational lensing, points to dark matter's hidden bulk warping the fabric of space itself. So what is it? The leading theory points to WIMP, weakly interacting massive particles. These hypothetical subatomic entities could be 1 billion times heavier than protons, barely bumping into ordinary matter except through gravity. Underground labs like SNOLAB in Canada and Italy's Gran Sasso have spent years hunting for them, using vats of liquid xenon as cosmic fishing nets, but so far nothing. Another contender, Action's ultralight particles so elusive they could pass through a lead wall the size of a galaxy without a whisper. Experiments like ADMCS are tuning into the universe like a radio, hoping to catch their faint signal. Yet with every null result, the mystery deepens. Could dark matter be primordial black holes forged in the chaos of the early universe? Or something even stranger, a shadow universe with its own invisible physics parallel to ours? The frustration and the thrill is that after nearly a century of searching, we're still grasping at shadows. Dark matter taunts us with its effects while refusing to reveal itself. And until it does, we're left staring at the night sky, knowing the vast majority of it is made of something we can't see, can't touch, and barely understand. A cosmic reminder that sometimes the universe's biggest secrets aren't written in the stars, but in the empty spaces between them. Just when dark matter had us questioning how much of the universe we could actually see, along comes its more mysterious cousin, dark energy. This isn't just some invisible mass lurking in the cosmos. No, dark energy is something far stranger, a force so powerful it's stretching the very fabric of space itself, pushing galaxies apart at speeds that defy logic. It all started with a bombshell discovery in 1998, when 2 teams of astronomers made the same jaw-dropping observation. The universe wasn't just expanding, it was accelerating. Picture this: by studying distant supernova cosmic explosions so bright they outshine entire galaxies, scientists noticed something bizarre. These stellar beacons weren't just dimming with distance as expected. They were fainter than they should have been, meaning space wasn't just growing, it was speeding up. Think of it like tossing a ball in the air, only to watch it shoot faster into the sky instead of falling back down. That's how counterintuitive dark energy is. Suddenly, Einstein's old idea of a cosmological constant, a sort of anti-gravity energy woven into space, didn't seem so far-fetched. But here's where things get really weird. Dark energy makes up about 68% of the universe's total energy budget, dwarfing even dark matter. Yet we have no clue what it actually is. Is it the energy of empty space itself, constantly bubbling into existence as the quantum foam of reality? Or is it some exotic, undiscovered field permeating the cosmos like an invisible fifth force? The leading theory points to the cosmological constant, a uniform energy density that doesn't dilute as space expands. but when scientists crunch the numbers, the predicted energy levels are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's the most embarrassing mismatch in physics. Dark energy doesn't just challenge our understanding, it rewrites the rules. Unlike dark matter, which pulls galaxies together with gravity, dark energy pushes them apart. It's a cosmic tug of war where the rope itself is growing longer, faster, with no end in sight. Some models suggest this acceleration could eventually tear atoms apart in a big rip. Others hint that dark energy might change over time, potentially reversing into a collapse. And then there's the terrifying possibility that we're seeing the first signs of a multiverse, where our pocket of reality is just one bubble among infinite others, each with its own physics. For now, dark energy remains the ultimate cosmic curveball. Every telescope from Hubble to the upcoming Vera C. Rubin Observatory is desperately scanning the skies for clues. But one thing's certain, whatever's out there, stretching the universe like taffy, it's forcing us to rethink everything we thought we knew. Dark matter might be the universe's hidden scaffolding, but dark energy, that's the unseen hand, flicking the lights on and driving reality itself toward an unknown destiny. Fast radio bursts are like the universe playing an elusive game of cosmic hide and seek. In just a few milliseconds, these mysterious signals release as much energy as the sun does in 80 years, then vanish without a trace. First detected in 2007, these bursts arrive from billions of light-years away, slamming into our telescopes with no warning and no discernible pattern. What makes them even more baffling, most appear once and never repeat, like a single, deafening knock echoing across the cosmos from an unknown sender. But then there's the outlier FRB 121102. Discovered in 2016, this burst didn't just flash once, it kept coming back. Dozens of repeat performances, sometimes in clusters, sometimes at random, all originating from a tiny galaxy 3 billion light-years away. Whatever's producing these repeating bursts isn't just destroying itself in a cataclysmic event. It's surviving, thriving even, and firing off signals like a celestial lighthouse with a broken dimmer switch. So what could possibly generate such intense, fleeting energy? The theories range from the spectacular to the downright speculative. Magnetars neutron stars with magnetic fields 1 trillion times stronger than Earth's top the list. Picture a stellar corpse so volatile it occasionally unleashes starquakes, cracking its crust and releasing tsunamis of radiation. Then there's the Blitzar hypothesis, a supermassive neutron star collapsing into a black hole, its death throes sending shockwaves across spacetime. Even cosmic string vibrations, defects in the fabric of reality left over from the Big Bang, have been floated as potential culprits. But let's address the elephant in the universe. Could FRBs be artificial? Some scientists, including Harvard's Avi Loeb, have dared to ask if we're seeing leakage from alien propulsion systems. Imagine a civilization harnessing the power of neutron stars to launch light sails across galaxies, their energy signatures briefly flickering into our detectors. Far-fetched maybe, but with no natural explanation fully fitting the data, the debate remains wide open. Here's the kicker: we're detecting more FRBs than ever, thanks to telescopes like CHIME in Canada, which spots dozens monthly. Yet each new burst seems to deepen the mystery. Some arrive with polarization twists hinting at extreme magnetic environments. Others come with lower frequencies, suggesting different origins entirely. It's as if the universe is taunting us, offering clues without ever revealing the full picture. One thing's certain: fast radio bursts are more than just cosmic static. They're intergalactic telegrams carrying encrypted details about the universe's most violent and possibly most inventive phenomena. And until we crack their code, these fleeting radio whispers will keep us guessing, reminding us that some of space's loudest statements are also its most enigmatic. Some stars flicker like candles in the wind, but then there's Tabby's star, a cosmic enigma that behaves more like a malfunctioning light bulb. Officially catalogued as KIC 8462852 and located 1,500 light-years away in the constellation Cygnus, this otherwise ordinary F-type star has been caught in the act of vanishing repeatedly, dramatically, and without explanation. Astronomers first noticed its odd behavior in 2015, when data from NASA Kepler Space Telescope revealed dips in brightness so extreme they defied all known stellar phenomena. We're not talking about the gentle dimming of a planet passing by. This star's light would plummet by up to 22%, as if something colossal were lumbering across its face. And then, just as mysteriously, it would brighten again. The initial theory pointed to a swarm of comets, thousands of them, perhaps orbiting the star in tight formation, their dusty tails blotting out its light. But calculations quickly tore that idea apart. To create such drastic dimming, you'd need more comets than our solar system has ever produced, all crammed into a single orbital path. Then came the galactic gasp heard round the internet. Could it be aliens? Astronomer Jason Wright floated the idea of a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harvest a star's energy. Imagine a vast network of solar panels, each the size of a continent, encircling Tabby's star like a cosmic spiderweb. It was a tantalizing thought, one that sent telescopes worldwide scrambling for a closer look. But when the SETI Institute trained its Allen telescope array on the star, hoping to catch leaked radio signals from extraterrestrial engineers, the universe offered only silence. Meanwhile, spectroscopic studies revealed another wrinkle: the dimming wasn't uniform. Some wavelengths of light were blocked more than others, suggesting the culprit wasn't solid megastructures but something far more diffuse. Dust perhaps, but not like the dust in our solar system. This material was fine, uneven, and constantly shifting, as if the star were coughing up immense clouds of debris on a whim. Now, years into the mystery, Tabby's star still refuses to follow a script. Some dimming events last for days, others for weeks. Some coincide with predictable cycles, others erupt unpredictably like stellar tantrums. The latest data from the Los Cumbres Observatory suggests the star might be consuming a planet, a messy, drawn-out process that could explain the erratic dimming. Others propose a massive asteroid belt pulverized by collisions into a swirling storm of shards. What makes this star so fascinating isn't just the what, but the how often. Most cosmic anomalies are one-offs of flukes we catch once and spend decades trying to explain. Tabby's star, though, it keeps performing. Every new observation adds another layer of intrigue, another possibility to weigh. Whether it's a natural process we've yet to discover or something far more extraordinary, one thing's clear: this isn't just a star. It's a question mark written in light, daring us to decode its secrets. And for now, those secrets remain stubbornly, brilliantly out of reach. Deep in the cosmic shadows, hidden behind the thick dust and stars of our own Milky Way, lurks a gravitational monster so powerful it's bending the fate of entire galaxies. They call it the Great Attractor, an unseen force dragging everything in our galactic neighborhood, including our Milky Way, toward it at a staggering 14 million miles per hour. Yet for decades, this colossal mystery remained invisible, tucked behind what astronomers call the zone of avoidance, a region so choked with interstellar gas and starlight that optical telescopes couldn't peer through. Discovery of this cosmic heavyweight began in the 1970s, when astronomers noticed something off about the motion of nearby galaxies. Instead of evenly expanding with the universe's overall flow, thousands of galaxies, including ours, were all streaming toward the same patch of sky near the constellations Centaurus and Hydra. It was as if space itself had a hidden downhill slope, and everything was sliding toward it. But what lay there? Initial estimates suggested a mass equivalent to tens of thousands of Milky Ways, concentrated in a region just 250 million light-years away. The real breakthrough came when scientists swapped optical telescopes for radio and X-ray observatories, piercing the zone of avoidance like cosmic sonar. What they found was even stranger than expected. The Great Attractor wasn't a single, dense object, it was a sprawling supercluster, a tangled web of galaxies and dark matter now known as the Laniakea supercluster, a Hawaiian term meaning immeasurable heaven. Our Milky Way sits on the fringes of this vast structure, like a leaf caught in a river's current. But here's the twist: Laniakea isn't the end of the story. Recent studies reveal an even larger force at play, the Shapley Attractor, a supercluster over 650 million light-years away, pulling Laniakea itself toward it. This means the Great Attractor might just be a waypoint in a far grander cosmic tug-of-war, a temporary eddy in an ocean of dark matter currents we're only beginning to chart. Mapping these invisible flows is like trying to reconstruct a hurricane by watching how leaves swirl. Projects like the Cosmic Flows Survey use the motions of thousands of galaxies to trace the gravitational undercurrents shaping our corner of the universe. Each new dataset adds another layer to the map, revealing a cosmos far more dynamic and far more mysterious than we ever imagined. The Great Attractor forces us to confront a humbling truth. Even as we unravel the universe's secrets, we're still just tiny passengers on a ride we don't fully understand. Every galaxy in our neighborhood is sailing toward an unseen horizon, pulled by forces hidden in the dark, and the destination that remains one of space's most tantalizing open questions. The universe is unimaginably vast, with 2 trillion galaxies, each hosting billions of stars, many surrounded by planets in the so-called Goldilocks zone where life could thrive. By sheer probability, Earth shouldn't be special. So where is everybody? That's the crushing weight of the Fermi Paradox, a question first posed by physicist Enrico Fermi over lunch in 1950. If intelligent life is likely, why haven't we found a single trace of it? Some answers are unsettling. The Great Filter theory suggests civilizations hit an invisible wall, a catastrophic event or self-destructive tendency that wipes them out before they can colonize the stars. Maybe nuclear war, climate collapse, or rogue AI acts as a galactic grim reaper. The terrifying part, we don't know if humanity has already passed the filter, like being the lone survivor of a cosmic minefield, or if our doom still lies ahead, lurking in some undiscovered technology or societal flaw. Other explanations lean toward cosmic humility. The zoo hypothesis posits advanced civilizations observe us like animals in a wildlife preserve, deliberately avoiding contact until we reach a certain maturity. Or perhaps intelligence itself is fleeting, a brief evolutionary spark that burns out quickly. Dolphins and octopuses are brilliant, but without opposable thumbs or fire, they'll never build radios. Maybe technological civilizations are like mayflies, destined to flame out before mastering interstellar travel. Then there's the darkest possibility: we're alone. Not just in our galaxy, but in the entire observable universe. Rare Earth theorists argue that while microbial life might be common, the chain of events needed for complex organisms, a stable star, a protective moon, plate tectonics, even luck, could be astronomically improbable. If true, the silence isn't eerie, it's inevitable, but the paradox cuts deeper. Recent discoveries of potentially habitable exoplanets, like those orbiting TRAPPIST-1, only amplify the tension. With projects like SETI scanning the skies and Breakthrough Listen analyzing millions of radio channels, the absence of signals feels louder than any message. Some scientists, like David Brin, suggest we might be early to the cosmic party, with intelligent life still evolving elsewhere. Others think we're simply not listening correctly. Maybe aliens communicate via neutrinos, quantum entanglement, or something beyond our comprehension. The Fermi Paradox isn't just about aliens, it's a mirror. Every possible solution forces us to confront humanity's place in the cosmos, whether we're destined for greatness, doomed to oblivion, or something in between. Until we hear that first hello, or confirm the crushing silence is permanent, the paradox remains the universe's most profound riddle, one that rewrites itself with every unanswered telescope scan. Oumuamua wasn't just another space rock, it was a cosmic interloper from another star system, tumbling through our solar system like a ghost ship adrift in the void. When astronomers first spotted it in October 2017, they assumed it was a run-of-the-mill comet or asteroid, but within days it became clear this visitor was anything but ordinary. For starters, its shape defied logic, 10 times longer than it was wide, spinning chaotically like a celestial cigar. Then came the real shocker: it was accelerating. Not from gravity or outgassing, as comets do, but as if some unseen force were nudging it along. Theories erupted. Could it be a shard of a shattered planet, ejected from a distant star system? Or a hydrogen iceberg sublimating invisibly in sunlight? But Harvard astrophysicist Avi Loeb dropped the bombshell that sent the scientific community into a frenzy. What if Oumuamua was artificial? His controversial solar sail hypothesis suggested the object's acceleration and peculiar shape matched what we'd expect from a lightweight, discarded propulsion device, a relic of alien technology drifting between the stars. Critics pushed back hard. The lack of radio signals or visible debris seemed to rule out an engineered object. Others argued that exotic natural explanations, like a fractal dust aggregate or a nitrogen iceberg from a Pluto-like world, could explain the anomalies without invoking aliens. But Loeb held firm, pointing out that Oumuamua's reflectivity was off the charts, 10 times shinier than typical solar system asteroids. And then there was its trajectory. It came from the direction of Vega, a star known to host exoplanets, and left without a trace, as if it had completed a flyby mission. The debate rages on because Oumuamua is now beyond our reach, streaking toward the outer solar system at nearly 200,000 miles per hour. We'll never get another look, never settle the argument definitively. That's what makes it so haunting. Whether it was a bizarre quirk of nature or a postcard from another civilization, Oumuamua forced us to confront a thrilling possibility that the universe might be littered with artifacts we're only beginning to recognize. And the next time an interstellar visitor arrives, we'd better be ready, because it might not just be passing through, it might be saying hello. When NASA Pioneer 10 and 11 spacecraft sailed beyond the orbits of Jupiter and Saturn in the 1980s, they carried humanity's hopes into the outer solar system, but they also carried a mystery. Mission controllers noticed something bizarre. Both probes were slowing down more than physics predicted. Not by much, just a fraction of a nanometer per second squared. But over decades and billions of miles, that tiny discrepancy ballooned into one of the most stubborn puzzles in space exploration, the Pioneer anomaly. At first, scientists assumed it was a simple engineering glitch. Maybe heat radiating from the probe's nuclear power sources was pushing back like an invisible hand, or perhaps fuel leaks were creating tiny, unplanned thrusts. But when researchers crunched the numbers, thermal radiation could only explain part of the deceleration. The rest seemed to defy Newton's laws themselves. The anomaly was so persistent and so consistent between both probes that some theorists dared to whisper the unthinkable. Were we seeing the first cracks in Einstein's theory of gravity? The implications were staggering. If the Pioneer anomaly hinted at undiscovered physics, it could upend our understanding of the cosmos. One radical idea proposed that gravity behaves differently at extremely weak accelerations, a concept called modified Newtonian dynamics, or MN. Others wondered if dark matter's gravitational tug was subtly altering the probe's paths. The most tantalizing and controversial hypothesis, that an unseen ninth planet, or even a primordial black hole lurked in the solar system's outskirts, its gravity gently braking the pioneers as they sailed into the void. Then, in 2012, a team of researchers painstakingly reconstructed the probe's heat emissions using decades-old blueprints and found their smoking gun. Asymmetric thermal radiation, particularly from Pioneer 11 main antenna, turned out to be the primary culprit. But here's the twist: even after accounting for heat, a whisper of the anomaly remained, about 1/3 of the original signal. Was it residual heat they hadn't modeled perfectly, or something deeper? The Pioneer anomaly's legacy endures because it embodies science at its most humbling. For 30 years, it taunted us with the possibility of revolutionary physics, only to reveal how easily overlooked details can mimic the extraordinary. Yet that unresolved fraction still lingers, a reminder that sometimes the universe's quietest mysteries are the ones that echo loudest. Imagine particles hurtling through space with so much energy, they make the Large Hadron Collider look like a toy. These are cosmic rays, subatomic bullets, mostly protons, slammed into existence by forces so violent they dwarf anything in our solar system. Some pack the punch of a major league fastball compressed into a single proton. And here's the kicker: we still don't know where most of them come from. The mystery began in 1912 when physicist Victor Hess took a high-altitude balloon flight and discovered ionizing radiation increased with altitude, proof it wasn't coming from Earth. Today, we know these rays bombard our planet constantly, with lower-energy ones originating from our Sun. But the real head-scratchers are the ultra-high-energy cosmic rays, or UHECA. These rare beasts carry energies exceeding 1 electronvolt, millions of times more powerful than anything our most advanced particle accelerators can produce. One detected in 1991, dubbed the "Oh my God" particle, had the kinetic energy of a bowling ball dropped from waist height, all crammed into a single proton. So what cosmic slingshot could fire particles with such insane energy? Supernovae were the first suspects. When massive stars explode, their shockwaves can accelerate particles to tremendous speeds. But even these stellar fireworks can't account for the most extreme UHECA. Enter active galactic nuclei and the cores of galaxies, where supermassive black holes devour matter, spewing jets of plasma at near light speed. These jets might act as natural particle accelerators, hurling protons across the universe like cosmic railguns. Yet there's a problem. The highest energy cosmic rays should be crippled by something called the Greisen-Zatsepin-Kuzmin-Gizike limit. According to physics, particles traveling such vast distances ought to lose energy by smashing into photons from the cosmic microwave background. But some UHECA laugh in the face of this limit, arriving with energies that should be impossible. One theory: they're coming from much closer than we think, perhaps from rogue, hyperactive black holes in our galactic backyard. Others speculate these particles are evidence of exotic physics, like decaying super-heavy dark matter or defects in spacetime itself. Detecting them is like playing celestial pinball. When UHECA hit Earth's atmosphere, they trigger air showers, cascades of secondary particles that spread over miles. Observatories like the Pierre Auger Array in Argentina catch these showers using tanks of water or fluorescent detectors, tracing the rays back to their origins. But here's the twist: the highest energy events point toward nothing. Empty patches of space with no obvious AGN or supernova remnants. It's as if the universe is flinging these particles from hidden cannons, teasing us with cosmic sleight of hand. What makes cosmic rays so thrilling isn't just their energy, it's their anonymity. They're cosmic fingerprints with no clear suspect, bullets fired from an unmarked gun. Every time we think we've pinned down their source, a new outlier arrives, defying the rules and sending theorists back to the drawing board. Until we solve the puzzle, these ultra-high-energy enigmas will keep raining down, silent reminders that the universe still holds cards it hasn't shown us. The cosmic microwave background is supposed to be the ultimate equalizer, a nearly uniform echo of the Big Bang. stretching across the sky like a fossilized snapshot of the infant universe. But when scientists mapped its subtle temperature fluctuations with unprecedented precision, they stumbled upon something that sent chills down the spines of cosmologists, a pattern eerily aligned with our own solar system. Dubbed the axis of evil, this bizarre cosmic coincidence doesn't just defy expectations, it threatens to upend one of astronomy's most sacred principles. The story begins with NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, which spent years scanning the heavens for minuscule temperature variations in the CMB, tiny ripples representing the seeds of future galaxies. According to the cosmological principle, these fluctuations should be randomly distributed with no preferred direction or alignment. The universe, after all, is supposed to look roughly the same in every direction. No center, no edges, no cosmic up or down. Yet when researchers analyzed WMAP data, they found a spine-tingling correlation. Several of the largest fluctuations lined up suspiciously well with the ecliptic plane, the same disk in which Earth and the planets orbit the Sun. It was as if the universe had scribbled an arrow pointing directly at us, whispering, "You are here." Skeptics rushed to dismiss it as a statistical fluke, a cosmic version of seeing faces in clouds. After all, with enough data points, something is bound to look coincidental. But then Planck, Europe's even more sensitive CMB observatory, confirmed the anomaly with sharper resolution. The axis persisted, stubbornly mocking the idea that our place in the cosmos was unremarkable. Suddenly, the question wasn't just about data quirks, it was about whether we'd fundamentally misunderstood the structure of reality. Could it be contamination from our own solar system? Solar winds or dust might theoretically imprint patterns on the CMB maps, but calculations show their effect would be far too weak to explain the axis. Others propose that the universe isn't as isotropic as we thought, that on the largest scales, space might have a subtle grain like cosmic wood, with structures aligning along invisible filaments. Some even float the radical idea that the Big Bang wasn't perfectly symmetrical, leaving behind a primordial twist in spacetime itself, but the most unsettling possibility. That we're seeing evidence of a pre-Big Bang universe, an older cosmos whose structure somehow imprinted itself on ours, like a shadow flickering through the curtain of creation. If true, the axis of evil isn't just an anomaly, it's a crack in the foundation of modern cosmology, a hint that the universe remembers something we've forgotten. And until we decipher its meaning, this ghostly alignment will keep staring back at us, a cosmic riddle written in the afterglow of time itself. Black holes aren't just cosmic vacuum cleaners, they're the ultimate testing grounds for physics, places where the rules of reality twist into knots. And nowhere is that more apparent than in the black hole information paradox, a puzzle so profound it pits Einstein against quantum theory in a battle neither can afford to lose. It all started with Stephen Hawking's groundbreaking realization in 1974. Black holes aren't completely black, they emit radiation, slowly evaporating over eons. But this brilliant insight came with a devastating catch. Hawking radiation appeared to erase information from the universe, violating one of quantum mechanics' most sacred principles. Here's the heart of the crisis. In the quantum world, information, the precise state of every particle, can never be destroyed. It might get scrambled like an egg, but you should always be able to trace it back to its original form. Yet when a black hole evaporates via Hawking radiation, calculations suggested all the data about what fell in, whether it was a star, a spaceship, or a library of encyclopedias, would vanish forever, leaving behind only generic thermal noise. It was as if the universe had a backdoor where the rules didn't apply, and physicists recoiled at the implication. Either quantum mechanics was wrong or general relativity was incomplete. Desperate for a solution, theorists proposed radical fixes. The firewall hypothesis suggested that at the event horizon, an invisible wall of searing energy might annihilate anything crossing it, preserving information but shredding Einstein's vision of smooth spacetime. Imagine diving toward a black hole only to hit a cosmic shredder instead of slipping seamlessly into the unknown. The idea horrified many, as it implied space itself had a memory, a violent one. Then came the holographic principle, a mind-bending alternative straight out of science fiction. Perhaps information isn't lost inside the black hole, but encoded on its two-dimensional surface like a cosmic DVD. Every particle falling in would leave a pixel on the event horizon, preserving data in a form we just haven't learned to read. This hologram theory, inspired by string theory, recasts the entire universe as a projection, a 3D movie playing on a 2D screen at the edge of reality. Recent breakthroughs have only deepened the intrigue. In 2019, physicists calculated that Hawking radiation itself might carry subtle quantum imprints of what fell in, like smoke preserving the shape of a burned letter. Meanwhile, experiments with quantum computers and lab-grown analogs of black holes suggest information might escape after all, just in forms we're only beginning to decipher. What makes this paradox so intoxicating isn't just the clash of theories, it's the stakes. If information can be destroyed, the entire framework of quantum mechanics collapses. If it can't, Einstein's elegant spacetime must bend to accommodate something even he couldn't foresee. Black holes, it seems, aren't just swallowing matter, they're forcing us to rewrite the textbooks. And until we solve their riddle, we're left staring into the abyss, wondering if the universe keeps secrets even physics can't uncover. The Moon today is a quiet, airless world, its surface scarred by craters, its magnetic field barely a whisper. But 4 billion years ago, it might have been a different story. Lunar rocks brought back by Apollo astronauts hold a startling secret. Some contain magnetic imprints suggesting the Moon once had a magnetic field up to 100 times stronger than Earth's does today. That's not just surprising, it's downright baffling. Magnetic fields usually require two key ingredients, a molten metallic core and rapid rotation to churn that core into a dynamo. Yet the Moon's core is tiny, its rotation sluggish. So how did it generate a magnetic powerhouse strong enough to leave fingerprints in ancient rock? One leading theory points to a cosmic collision, literally. In the Moon's infancy, debris from a massive impact might have superheated its mantle, creating turbulent convection currents that stirred residual liquid metal in its core. Think of it like stirring a cup of coffee with a spoon. The motion generates temporary currents. Some models suggest this impact-driven dynamo could have sustained a magnetic field for a few 100 million years before fizzling out. But there's a problem. Not all lunar rocks from that era show magnetism. If a dynamo was at work, why the patchy record? Then there's the core crystallization hypothesis. As the Moon's molten interior cooled, heavier elements like iron might have solidified first, releasing lighter material upward in a process called compositional convection. This rising material could have acted like a planetary scale mixer, keeping the core churning longer than expected, like a lava lamp with molten metal instead of wax. But simulations show even this process shouldn't have lasted long enough to explain the strongest magnetic signatures found in Apollo samples, the real curveball. Some rocks display magnetism after the Moon's dynamo should have died. That's led to wilder ideas like plasmasphere induction, where charged particles from the young sun's violent solar winds interacted with the Moon's tenuous atmosphere, creating fleeting magnetic bubbles. It's a stretch, but not impossible. Others speculate the Moon's crust itself became temporarily magnetized during massive asteroid impacts, like hitting a cosmic reset button on its magnetic memory. But the most tantalizing clue might lie in anorthosite, a light, floaty rock that forms in magma oceans. Some lunar anorthosites are magnetized, hinting the Moon's field was active while its surface was still molten. If true, the dynamo wasn't just powerful, it was ancient, sparking to life in the Moon's first 100 million years. That timing overlaps with when Earth's own magnetic field was strengthening, raising a provocative question. Did our planet's gravity tugging on the Moon's core play a role? The Moon's magnetic mystery isn't just academic. Unraveling it could rewrite how we understand small planetary bodies across the cosmos, exomoons included. Maybe dynamos don't always need massive cores. Maybe impacts or tidal forces can kickstart magnetism in unexpected ways. Every new lunar sample, every refined computer model peels back another layer of the puzzle. And until we crack it, those magnetized moon rocks will keep whispering secrets about a time when Earth's pale companion was anything but quiet. At Saturn's North Pole, a storm rages with a shape so perfect it looks almost artificial. A colossal hexagon, wider than two Earths, spinning like a cosmic gear for decades without losing its form. Discovered by Voyager in the 1980s and studied in detail by Cassini, this six-sided jet stream defies everything we know about planetary weather. On Earth, storms spiral chaotically, governed by fluid dynamics that favor curves, not corners. Yet here, etched into Saturn's atmosphere with razor-sharp precision, is a polygon so stable it's outlasted multiple generations of telescopes. What makes this hexagon so hypnotic isn't just its geometry, it's the contrast between its rigid structure and the turbulent chaos inside. Infrared images reveal a roiling vortex at its center, with winds screaming at 320 miles per hour, yet the hexagon's edges remain eerily crisp. It's like watching a bullet ricochet inside a perfectly etched glass jar. Scientists initially suspected some kind of standing wave pattern, where atmospheric oscillations lock the storm into this shape. But lab experiments tell a stranger story. Researchers at Oxford recreated scaled-down versions using a spinning water tank, tinted to visualize flows. When the rotation speed hit a sweet spot, something magical happened. The swirling fluid spontaneously organized into polygons, first hexagons, then octagons, even triangles. The key: differences in flow speed between adjacent atmospheric bands. On Saturn, where jet streams shear past each other at varying velocities, these shear zones may act like invisible walls, trapping turbulence into geometric prisons. Yet Earth's own jet streams, though fast, never settle into such perfect shapes. The difference lies in scale and simplicity. Our planet's weather is muddled by oceans, mountains, and a thick, restless atmosphere. Saturn, by contrast, is a gas giant with no solid surface to disrupt the flow, just endless layers of hydrogen and helium, spinning uniformly like a vast liquid machine. Add to that Saturn's tilt and seasonal changes, which bathe the pole in sunlight for years, possibly reinforcing the hexagon's stability. The hexagon isn't just a curiosity, it's a masterclass in emergent order. Nature, under the right conditions, can produce precision without blueprints, symmetry without architects. And as Cassini's data continues to be analyzed, new wrinkles emerge. Some studies suggest the hexagon plunges hundreds of miles deep, anchoring itself in Saturn's hidden depths. Others hint at harmonic oscillations that keep the structure tuned like a vibrating guitar string. What we're witnessing might be more than a storm. It could be a window into the fundamental physics governing fluid behavior across the cosmos. From Jupiter's polar cyclones to the swirling disks of newborn solar systems, patterns like Saturn's hexagon might be hiding in plain sight, waiting for us to recognize the universal language of whirls and edges. Until then, that six-sided sentinel keeps spinning, a reminder that even in chaos, the universe has a knack for geometry. Most of the cosmos hums with the glow of galaxies clustered together like fireflies in the night, but not the Boots void. Stretching an unfathomable 330 million light-years across, this cosmic dead zone is so empty, so hauntingly barren, that astronomers initially thought their instruments were broken. Imagine a sphere of nothingness so vast it could swallow thousands of Milky Ways whole, leaving behind only a chilling, galaxy-free expanse. This isn't just a gap in the cosmic web, it's a screaming anomaly that defies everything we know about how the universe builds itself. The void was first spotted in the 1980s when surveys mapping galaxy distributions kept hitting a blank spot in the constellation Bootes. At first, researchers assumed it was an observational fluke, maybe dust clouds or instrument errors were blocking the view. But as telescopes grew sharper, the truth became undeniable. This wasn't a mistake. It was a genuine nothingness, a pocket of space where galaxies should have been but weren't. To put its scale into perspective, if you placed the Milky Way at its center, the nearest galaxy would be so far away, our night sky would appear almost starless. Theories scrambled to explain how such a void could exist. In the standard model of cosmic structure formation, gravity pulls matter into filaments and clusters, leaving behind smaller, bubble-like voids, but nothing on this scale. Bootes is 7 times larger than any void predicted by simulations. One radical idea suggests it's the imprint of an ancient collision between our universe and another, bubble in the multiverse, a crash so violent it cleared out everything in its path. Others propose it's evidence of cosmic defects, kinks in space-time, left over from the Big Bang that repelled matter like a magnetic field pushing away iron filings. But here's the eerie twist: the void might not be completely empty. Deep in its heart, a handful of lonely galaxies drift like castaways, their isolation deepening the mystery. How did these stragglers survive the purge? Were they flung there by gravitational slingshots, or are they remnants of a larger structure that somehow avoided annihilation? Each one raises new questions about whether the void formed through slow, steady evaporation or some cataclysmic event we haven't imagined yet. The Bootes void does more than puzzle astronomers. It forces us to rethink the universe's architecture. If structures this vast can exist, what other anomalies lurk in the unseen darkness? And if voids aren't random but signatures of deeper physics, their silence might be the loudest clue yet that our cosmic map is missing whole chapters. For now, this celestial dead zone remains a quiet revolution, a blank page in the story of everything, waiting for its secrets to be uncovered. Rising from the dust and gas of interstellar space like an otherworldly cathedral, the Red Rectangle Nebula stands as one of the most geometrically perfect structures in the cosmos. Located about 2,300 light-years away in the constellation Monoceros, this celestial oddity earned its name from early astronomers who saw it through ground-based telescopes, a vivid red rectangle floating against the black velvet of space. But when the Hubble Space Telescope turned its gaze toward it, the truth proved even stranger. Twin cones of glowing gas intersecting to form an almost flawless X-shape, with ladder-like rungs stretching between them like the steps of a cosmic ziggurat. This isn't how nebulae usually behave. Most billow into chaotic, organic clouds sculpted by stellar winds, not crisp angles that look drafted by an unseen architect. At the heart of this enigma lies HD 44179, a dying star caught in the act of shedding its outer layers. Most aging stars create spherical planetary nebulae as they puff away material evenly in all directions. But the Red Rectangle's progenitor star seems to be playing by different rules. Observations reveal it's actually a close binary system, 2 stars locked in a tight orbital dance, their gravitational waltz possibly funneling ejected gas into those startling geometric cones. This dance also produces another puzzle: vast amounts of peculiar hydrocarbon molecules called polycyclic aromatic hydrocarbons, or PAH. These complex carbon-based compounds, normally found in soot or engine exhaust on Earth, glow an eerie red under ultraviolet light, painting the nebula its signature hue. Yet their sheer abundance here is bizarre. Space is no stranger to complex molecules, but the Red Rectangle contains more PAHs than any known nebula, as if someone spilled an interstellar oil slick across its rungs. Then there's the light itself. Unlike most nebulae which scatter light randomly, the Red Rectangle polarizes its glow with near-perfect alignment, like sunlight reflecting off a still lake. This suggests its dust grains are unnaturally uniform, possibly shaped by intense magnetic fields or some undiscovered process in the binary star's death throes. Some researchers speculate the ladder-like rungs might be shock waves from periodic ejections, frozen in time like ripples in a pond. Others wonder if we're witnessing the birth of a new kind of cosmic architecture, where binary stars and chemistry conspire to build structures far more ordered than nature typically allows. But the greatest mystery might be what comes next. As the central stars continue to evolve, the red rectangle won't stay red forever. Its rich carbon content hints at a future where these molecules could coalesce into something even rarer, a nursery for complex organic compounds, the raw ingredients of life. Whether by chance or some deeper physics, this nebula seems to be assembling the pieces of a cosmic recipe we've only begun to read. And until we unravel how a dying star's tantrum became a geometric masterpiece, the red rectangle will keep its secrets locked in light and dust, a surreal monument to the universe's flair for the unexpected. Galaxies are supposed to play by cosmic rules, spinning under the invisible grip of dark matter, their stars held in check by its gravitational glue. But NGC 1052DF2 isn't just breaking the rules, it's shredding them. This bizarre, ghostly galaxy, floating 65 million light-years away in the constellation Cetus, does the unthinkable. It appears to have almost no dark matter at all. When astronomers first measured its star's movements in 2018, expecting the usual telltale signs of dark matter's pull, their data came back clean. The stars were drifting lazily, barely moving, as if suspended in zero gravity. It was like tossing a handful of confetti into the wind and watching it drop straight to the ground, defying every law of cosmic aerodynamics. The discovery sent shockwaves through astrophysics. Dark matter isn't just a minor ingredient in galaxies, it's the scaffolding that holds them together. Take it away, and conventional physics says a galaxy like DF2 should have disintegrated eons ago, its stars scattering into the void like marbles spilled across a floor. Yet here it is, a cosmic rebel flaunting its defiance. Some researchers scrambled to explain it as a fluke. Maybe DF2 was born from a freak gas collision, or perhaps its dark matter was violently stripped away by a neighboring galaxy's gravity. But follow-up observations only deepened the mystery. The galaxy's globular clusters, dense balls of ancient stars orbiting its edges, were moving just as sluggishly as its stars. If dark matter were present, those clusters should have been whipping around like planets on a cosmic racetrack. Their lethargy was a smoking gun. DF2's dark matter wasn't hiding, it was missing. Then came the plot twist. In 2021, astronomers found a second dark matter-deficient galaxy, NGC 1052DF4, lurking nearby. Two outliers might still be coincidence, but a pattern, that's a problem. Critics argued that distance measurements to these galaxies could be off, skewing calculations. Others proposed that DF2's dark matter might be heated up, scattered by some violent event into a diffuse halo too faint to detect. But the most provocative idea, that these galaxies aren't mistakes, their proof dark matter can be decoupled from visible matter entirely, challenging the very foundation of how we think galaxies form. The implications are staggering. If galaxies can exist without dark matter, it means the universe might have more than one recipe for building them. Perhaps DF2 and DF4 are cosmic tumbleweeds, born in environments so sparse that dark matter never clustered around them. Or maybe they're the shattered remnants of a larger galaxy, their dark matter stolen in some ancient collision we've yet to uncover. Whatever the answer, these ghostly galaxies are forcing us to confront an uncomfortable truth. Dark matter might not be as universal as we thought. And in that uncertainty lies the thrill of discovery, the chance that even our most fundamental assumptions about the cosmos might need rewriting. For now, DF2 stands as a cosmic riddle, a silent challenge to the textbooks. Every new observation, every refined simulation brings us closer to cracking its code. But until we do, this enigmatic galaxy serves as a reminder. The universe doesn't just follow rules, it makes them. And sometimes it breaks them just to see if we're paying attention. Somewhere between the particles we know and the shadows we don't, there might exist something even stranger, an entirely new form of matter that doesn't play by the standard rules of physics. Meet the unparticle, a hypothetical substance so bizarre it could rewrite our understanding of reality itself. Theorized by physicist Howard Georgi in 2007, unparticles don't behave like protons, electrons, or any familiar building blocks of the universe. Instead, they exist in a quantum limbo, neither fully particles nor pure energy, flickering in and out of detectability like cosmic ghosts. What makes unparticles so revolutionary isn't just their strangeness, it's what they could explain. Dark matter's gravitational grip and dark energy's relentless push both defy conventional physics. But unparticles, with their ability to interact weakly or not at all with ordinary matter, might finally offer a unified solution. Picture this: invisible fields of unparticle stuff permeating the cosmos, exerting subtle forces that masquerade as dark energy or clustering in halos around galaxies like dark matter. Because unparticles aren't tied to fixed masses or energies, they could manifest in infinitely variable ways, some dense enough to bend light, others so diffuse they nudge space itself apart. The hunt for these elusive entities is already underway in the world's most powerful labs. Particle colliders like the Large Hadron Collider are probing high-energy crashes for anomalies, missing energy, or skewed collision angles that might hint at unparticles slipping undetected through sensors. Meanwhile, ultra-precise experiments measuring gravitational waves or neutron behavior could spot distortions caused by unparticle fields warping spacetime itself. Even cosmic rays, those high-energy messengers from distant galaxies, might carry fingerprints of unparticle interactions if we learn how to read them. But here's the catch: unparticle physics isn't just about finding a new particle. It's about discovering a whole new sector of reality, a hidden layer operating under rules we haven't even imagined. If they exist, unparticles might not just solve dark matter and energy. They could reveal a universe far richer, far weirder than our textbooks ever dared to suggest. The search isn't just about filling gaps in our knowledge, it's about tearing those gaps wide open and glimpsing what lies beyond. For decades, whispers have swirled about an enigmatic object silently circling our planet, the so-called Black Knight satellite. Described as a 10,000-year-old alien artifact lurking in Earth's orbit, this legend has inspired everything from sci-fi novels to breathless conspiracy documentaries. The story goes like this. In 1960, radar operators detected an unknown object shadowing Sputnik, and astronomers later claimed it was in polar orbit, a trajectory considered impossible for human-made satellites at the time. Then came the clincher: alleged transmissions intercepted in the 1920s, dubbed the Black Knight broadcasts, interpreted by some as extraterrestrial SOS signals. The mythos grew with grainy NASA photos from the 1990s, said to show a mysterious dark shape floating near the space shuttle. But peel back the layers and the truth proves far stranger than fiction. The Black Knight isn't a single entity, it's a chaotic jumble of misidentified space debris, optical illusions, and good old-fashioned storytelling. Those eerie 1920s radio signals, almost certainly early experiments in long-range radio echo, bouncing signals off the ionosphere, a phenomenon later harnessed for radar. The alien satellite spotted in 1960, likely fragments from a Discoverer spy satellite launch, scattered across orbit like cosmic confetti. As for those infamous NASA photos, agency officials have identified them as thermal blankets lost during spacewalks, their crumpled shapes twisting in sunlight to resemble something out of a ufologist's dream. Yet even skeptics admit there's a tantalizing grain of mystery here. The Earth is surrounded by a graveyard of defunct satellites and rocket parts, over 29,000 tracked objects larger than 4 inches with countless smaller fragments. Some, like the lost glove of Gemini astronaut Ed White or the discarded Hasselblad camera from Apollo 12, are human artifacts adrift in the void. Others, like the upper stage of a 1958 Vanguard rocket, still silently circle the planet, older than most space agencies. Could one of these relics have been mistaken for something more sinister? Absolutely, but that doesn't entirely explain why certain orbital oddities, like the object catalogued as 1991-06-03, which vanished from radar, still resist easy classification. What makes the Black Knight legend endure isn't just the allure of ancient astronauts, it's the unsettling reality that our planet's orbit is filled with unknowns. Every year, new debris is spotted, some defying immediate explanation. Most turn out to be mundane, but a handful, like the baffling WTF object spotted in 2018, remain officially unresolved. The universe, it seems, enjoys dangling just enough ambiguity to keep us wondering. Whether the Black Knight was ever more than a myth, its legacy endures as a reminder that sometimes the line between fact and fantasy thins to a hair's breadth in the vast, silent dark above us. Mars should not have methane, at least not the way we're finding it. This simple gas, often belched by living organisms on Earth, keeps flickering in and out of detection in the Martian atmosphere like a cosmic Morse code we can't decipher. When NASA Curiosity rover first sniffed traces of methane in 2013, the scientific community erupted. Here was a tantalizing possibility. Was this gas a whisper of ancient or even present Martian life? Or just another geological quirk from a planet that refuses to play by Earth's rules? Curiosity's findings were maddeningly inconsistent. The methane didn't linger like a steady atmospheric component. It spiked unpredictably, sometimes jumping to 10 times background levels before vanishing within weeks. These bursts defied easy explanation. On Earth, 95% of methane comes from biological sources, everything from cow guts to decaying swamps. But Mars lacks cows, swamps, or any obvious signs of life. That left two possibilities. Either something underground was producing methane right now, or the gas had been trapped for eons in icy reservoirs, occasionally leaking when temperatures shifted. The biological camp points to extremophiles, microbes that thrive in Earth's harshest environments, from volcanic vents to Antarctic ice. If similar organisms existed on Mars, they might metabolize hydrogen and carbon dioxide, exhaling methane as a byproduct. The fact that methane levels rise during warmer seasons hints at something active beneath the surface, reacting to environmental changes, but the geological counterargument is just as compelling. Serpentinization, a process where water reacts with certain rocks, can produce methane without any biology involved. Mars's ancient volcanic past might have left pockets of methane-rich minerals slowly venting when disturbed. The plot thickened when Europe's trace gas orbiter, designed specifically to map Martian methane, found nothing. Its ultra-sensitive instruments scanned the planet for years without detecting the gas globally, contradicting Curiosity's ground-level spikes. This discrepancy sparked a detective story. Was the orbiter missing something? Were methane plumes so localized that they dissipated before reaching high altitude? Or was Curiosity itself somehow producing false positives, though engineers ruled out contamination repeatedly? Now, new players are joining the hunt. NASA Perseverance rover carries instruments to correlate methane spikes with other chemical signatures, while future missions like the Mars Life Explorer aim to drill deeper than ever before. Every flicker of methane rewrites the question, are we seeing chemistry or the faint, stubborn heartbeat of life next door? Until we crack this riddle, Mars keeps its secrets close, teasing us with whiffs of a gas that could mean everything or nothing at all. If you think the Boots void is unsettling, wait until you meet its polar opposite, the Hercules Corona Borealis Great Wall. a galactic superstructure so vast it shouldn't exist. Stretching an incomprehensible 10 billion light-years across, this cosmic behemoth isn't just a cluster of galaxies, it's a filament of reality itself, weaving through the universe like a thread through cloth. Discovered in 2013 by mapping gamma-ray bursts, the Great Wall defies one of astronomy's most sacred rules, the cosmological principle which states that on large scales, the universe should look roughly the same in every direction. But this titanic structure throws that assumption out the window. Imagine tossing a handful of sand into the wind and watching it arrange itself into a perfect arrow pointing east. That's the level of cosmic defiance we're dealing with. What makes this wall so revolutionary isn't just its size, it's the timing. According to the Big Bang Theory and cosmic inflation, the universe didn't have enough time in its early epochs to form structures this enormous. Inflation, the rapid expansion of space in the first fractions of a second after the Big Bang, should have smoothed out matter into a more uniform distribution. Yet here we are, staring at a galactic scaffolding that seemingly ignored the rulebook. Some theorists argue it might be a statistical fluke, a chance alignment of smaller structures that looks connected from our vantage point. But the data tells a different story. Gamma-ray bursts, the death cries of massive stars, trace the wall's outline with eerie precision, marking it as a real, coherent feature. The Great Wall isn't just a challenge to theories, it's a window into the universe's hidden architecture. Could it be a fossil from pre-inflation, a relic of quantum fluctuations frozen into the fabric of space-time, or evidence of exotic physics like cosmic strings, defects in reality left over from the universe's birth? Some even speculate it's the shadow of a higher dimensional structure, a wrinkle in the cosmic canvas we're only seeing edge on. Every telescope trained on it peels back another layer of mystery, but the deeper we look, the more questions arise. For now, the Hercules Corona Borealis Great Wall stands as a silent rebuke to our models, a reminder that the universe might be less predictable and far more wondrous than we ever imagined. It's not just a structure, it's a question written across 10 billion light-years, waiting for us to find the answer. There's a spot in the cosmic microwave background where the universe seems to have left the freezer door open, an eerie cold patch spanning nearly 1 billion light-years in the constellation Eridanus. This isn't just a minor temperature dip, it's a cosmic chill so profound that standard physics struggles to explain it. When scientists first mapped the CMB with NASA's WMAP satellite, they expected tiny fluctuations, the primordial wrinkles of the Big Bang. But the Eridanus cold spot stood out like an icy thumbprint, 7 times colder than surrounding regions. At first, astronomers brushed it off as a statistical fluke. Then Planck, Europe's ultra-precise CMB observatory, confirmed it. This anomaly was real and it demanded answers. One radical theory suggests we're seeing the shadow of another universe. In certain multiverse models, neighboring bubble universes could gravitationally push against ours during cosmic inflation, leaving behind underdense regions, cosmic bruises where less matter clustered. Picture 2 soap bubbles barely touching. The dent where they meet might resemble the Eridanus void. Supporters point to the spot's unusual lack of galaxies, as if something had scooped out the cosmic stuffing. If true, this could be our first indirect evidence of a parallel reality, forever separate yet imprinted on our sky. But quantum physics offers a less exotic, if equally mind-bending alternative. The cold spot might be a rare, ultra-large quantum fluctuation frozen into space-time during the universe's first trillionth of a second. Inflation theorists calculate that while such massive fluctuations are improbable, they're not impossible in an infinite universe. Think of it like rolling dice. Given enough throws, you'll eventually get a string of 100 sixes. The Eridanus anomaly could simply be our cosmic dice landing on that 1 in a million combo. The debate hinges on extreme physics. If the void contains unusual patterns of polarized light or peculiar galaxy distributions, it could hint at multiverse origins. Current surveys like the Dark Energy Spectroscopic Instrument are mapping the void's 3D structure with unprecedented detail, searching for telltale signs of an external gravitational tug. Meanwhile, simulations of quantum fluctuations help refine how often supervoids this size should appear naturally. What makes the Eridanus cold spot so captivating isn't just its temperature, it's the sheer scale of possibilities it represents. Whether a window into the multiverse or a statistical cosmic hiccup, this frigid anomaly reminds us that even the universe's oldest light can still hold shocking secrets. And until we crack its code, that icy patch will keep taunting us with questions we're only beginning to ask. For centuries, travelers and astronomers have reported a ghostly glow stretching from the horizon after sunset or before dawn, a faint triangular light so delicate it was once mistaken for the first hint of sunrise. This is the zodiacal light, a cosmic whisper painted across the night sky, following the same path the planets travel. But unlike the auroras or Milky Way, this glow doesn't come from distant stars or atmospheric fireworks. It's far closer to home, a shimmering veil of dust floating right in our own solar system, lit up by sunlight like a celestial lantern. The source of this ethereal glow has puzzled scientists for generations. For decades, the prevailing theory pointed to comets' icy wanderers leaving dusty trails as they melt near the sun. Others suggested it was debris from asteroid collisions, rocky shrapnel scattered along the ecliptic plane. But when researchers calculated how much dust should be out there based on these sources, the math didn't add up. The zodiacal light shines twice as bright as it should, as if the solar system's attic holds far more dust than anyone anticipated. Recent discoveries have only deepened the mystery. NASA Juno spacecraft on its way to Jupiter made an unexpected detour measuring the dust cloud's density. The results were startling. Instead of a smooth distribution, the dust forms a dense, lopsided band concentrated near Mars's orbit. This clumpiness hints at something more violent than gentle comet shedding, perhaps a massive asteroid collision in the not-too-distant past. Imagine two mountain-sized rocks smashing together 1,000,000 years ago, scattering enough debris to outshine every comet combined. But here's where it gets weirder. Some of this dust doesn't behave like typical solar system debris. Tiny particles, no larger than smoke grains, spiral inward toward the sun at speeds that defy gravity's tug. One theory suggests electromagnetic forces driven by solar wind are flinging them like cosmic pinballs. Others propose these motes are interstellar hitchhikers, dust from beyond our solar system caught in the sun's pull. The zodiacal light isn't just a pretty sky phenomenon. It's a forensic snapshot of chaos, a record of collisions, migrations, and processes we're only beginning to understand. Every photon of that glow carries clues about the solar system's hidden history, written in dust we've yet to fully decode. And until we do, that eerie triangle of light will keep glowing, a silent testament to the violence and beauty simmering just beyond our planet's shadow. We can count the stars, map the galaxies, and even weigh black holes, but somewhere between all that visible cosmic splendor, half the universe's ordinary matter has gone missing. Not dark matter, not some exotic particle, but the very protons and neutrons that make up everything from planets to people. This is the missing baryon problem, and it's one of the most embarrassing accounting errors in modern astrophysics. If the universe's ledger were a spreadsheet, we'd be staring at a glaring discrepancy. Roughly 50% of the expected normal matter is simply unaccounted for. The mystery started with the Big Bang. By measuring the cosmic microwave background, scientists calculated exactly how much baryonic matter, ordinary stuff like atoms, should exist in the universe today. Then they tallied up all the visible galaxies, stars, and gas clouds. The numbers didn't just disagree, they were off by a staggering margin. Imagine inventorying a warehouse and realizing half the expected contents had vanished without a trace. Early theories proposed the missing matter might be locked in faint dwarf galaxies or drifting as cold gas between stars. But even after scouring the cosmos, the deficit remained, taunting astronomers like a cosmic magic trick with no reveal. Enter the warm, hot intergalactic medium, or Oumuamua, a theoretical web of diffuse gas threading the spaces between galaxies, so tenuous and hot it's nearly invisible. Picture steam rising from a boiling pot, but on a scale so vast it fills the voids between galaxy clusters. This gas isn't cold enough to form stars or dense enough to glow brightly. Instead, it simmers at temperatures between 100,000 and 10 million degrees, emitting faint X-rays rather than visible light. Detecting it is like trying to spot a single lit match in a foggy football stadium. The hunt for the Oumuamua has pushed telescopes to their limits. Some of the sharpest evidence comes from quirks in the light of distant quasars. As their beams pass through the cosmic web, certain wavelengths get absorbed by ionized oxygen in the Oumuamua, leaving fingerprints in the spectra. It's like shining a flashlight through mist and seeing where the beam dims. Other clues come from the Sunyaev-Zeldovich effect, where the cosmic microwave background gets slightly distorted as it passes through hot gas clouds. Each observation adds another piece to the puzzle, suggesting the Oumuamua might hold the bulk of the missing baryons, just in a form we've barely begun to see. Yet even with these breakthroughs, the Oumuamua remains elusive. Its gas is so thinly spread that current telescopes can only detect it in the densest filaments. Some researchers speculate part of the missing matter could be hiding in even stranger forms, perhaps as rogue planets drifting between stars or as ultrafast particles ejected by supernova. Others wonder if our models of the early universe are subtly off, overestimating how much matter should exist today. What makes this search so riveting isn't just the mystery, it's the scale of the oversight. We're not talking about a few misplaced atoms. This is half the ordinary matter in the cosmos, the very building blocks of reality, playing an endless game of hide and seek. And until we develop telescopes sensitive enough to map the Oumuamua faint glow or invent new ways to trace its ghostly tendrils, the universe's ledger will keep taunting us with its unbalanced books, a reminder that even the most fundamental truths can slip through our fingers like interstellar smoke. If you think empty space is truly empty, think again. The quantum vacuum is a seething, bubbling sea of energy so fundamental to reality that without it, the universe as we know it wouldn't exist, yet its very nature defies everything physics predicts. Imagine the void between stars not as a blank slate, but as a roiling ocean where particles flicker in and out of existence so fast we can barely catch their shadow. These virtual particles borrow energy from nothingness itself, popping up in particle-antiparticle pairs before annihilating in bursts of quantum fireworks. This isn't just theoretical whimsy. We've measured their effects in lab experiments like the Casimir effect, where two metal plates placed incredibly close together feel a mysterious push from these ghostly particles crowding the space between them. Here's where the math goes haywire. When physicists try to calculate how much energy this quantum vacuum should contain, their equations spit out a number so absurdly huge it would have ripped the universe apart nanoseconds after the Big Bang. We're talking about a discrepancy of 120 orders of magnitude, a 1 followed by 120 zeros between prediction and observation. It's like calculating the weight of a feather and getting an answer heavier than all the stars in every galaxy combined. This nightmare of mismatched numbers is called the cosmological constant problem, and it's been haunting theoretical physics since Einstein first proposed his infamous greatest blunder. The stakes couldn't be higher. This vacuum energy isn't just a curiosity, it's the leading candidate for dark energy, that mysterious force accelerating the universe's expansion. But if quantum mechanics says empty space should be brimming with immeasurably more energy than we observe, why is its actual effect so subtle? Some theorists suggest an unfathomably precise cancellation mechanism where positive and negative vacuum energies somehow balance to near perfection across the cosmos. Others propose radical revisions to quantum field theory itself, introducing supersymmetry or extra dimensions to tame the runaway equations. Then there's the chilling possibility that we're seeing evidence of the multiverse. In this scenario, countless universes exist with random vacuum energy values, and we just happen to occupy the rare one where the number is small enough for galaxies and life to form. It's like winning a cosmic lottery where nearly all tickets lead to instant cosmic collapse or eternal emptiness. What makes the quantum vacuum so mesmerizing is how it turns nothingness into something profound. The emptiest places in the universe might hold the keys to its ultimate fate, whether it keeps expanding, collapses back on itself, or tears apart in a big rip. Until we solve this riddle, every cubic centimeter of so-called empty space remains a battleground where our two most successful theories, quantum mechanics and general relativity, clash violently, neither willing to surrender. The vacuum isn't empty. It's screaming with unanswered questions. From the eerie silence of the Fermi Paradox to the inexplicable geometry of Saturn's hexagon, we've journeyed through 25 cosmic mysteries that defy even our boldest scientific theories. Each one, the wow signal's singular whisper, dark matter's invisible grip, Oumuamua's interstellar intrigue, serves as a humbling reminder. The universe isn't just stranger than we imagine, it's stranger than we can imagine. These aren't gaps in our knowledge, they're chasms, yawning open to reveal how much we've yet to discover. Consider this: every time we solve one cosmic riddle, 3 more emerge. The great attractor pulls us toward unseen masses. Fast radio bursts flicker like Morse code from alien civilizations we may never comprehend, and the quantum vacuum thrums with energy we can't begin to harness. Even our most advanced tools, telescopes that peer back to the dawn of time, particle colliders that recreate the Big Bang's fury, only scratch the surface of reality's full spectacle. Yet here's the beautiful truth: these mysteries aren't walls but doors. Each unanswered question is an invitation to explore further, to question deeper. Maybe you're drawn to the chilling void of Boots or the mathematical perfection of the red rectangle. Perhaps Tabby's star's flickers or the missing baryons keep you up at night. Whatever sparks your cosmic curiosity, remember, you're part of a human story that's always reached for the stars. So let's keep wondering together. Drop your favorite mystery in the comments. Is it the Black Knight's enduring legend, Mars methane whispers, or something we didn't cover today? Hit subscribe if you're hungry for more deep dives into the universe's greatest puzzles, because the cosmos isn't finished surprising us, and the next big revelation might just come from you. Keep looking up. The greatest discoveries aren't behind us, they're out there waiting.